Okay, now I found it. Right. Yeah, it is now again recorded, and we continue. So we right. I found it, and it is already. I hope it is recorded again. Right. So we finished with this story about Pythagoras, and the next topic, also very important, is dual basis. Dual basis, also very specific for tensor algebra, and you will see it is even sometimes much more convenient to use this dual basis even in comparison to the orthonormal basis. Let us discuss this topic of dual basis, and we should stop a little bit earlier because I would like to discuss with you very shortly these exercises, right? Okay, let us assume that we have a basis G. We have a basis G, G1, G2, Gn. And then let us consider another basis Gj, G dash, excuse me, and you see the difference. Here I write, in order to distinguish between two bases, I write here indices above. In the chapter 2, right, in the second part of the semester, we will discuss with you the difference. There is a deeper, let's say, difference between above indices and below indices, but now it's simply only to distinguish between these two bases. And this basis G dash should satisfy the following condition. As the scalar product of our initial vectors Gi and this delta should be and this new base G dash should be equal to chronicle delta. Seems to be the same as the orthonormal base, but not the case, because in the case of orthonormal base, what's the basis itself? We multiplied EI again with EJ, right, with the same basis. And here we have two different bases, right? We have two different bases, G and G dash. And this is the difference. That means that these vectors will still be orthogonal, but they should not be unit vectors. And this orthogonality is varied only between first basis and the second, original basis and dual basis. Right? The question is first is again to prove, does such a dual basis exist or not? Is it unique or not? Because if there are maybe two or more such bases, all dual to our original basis, it is not convenient, right? And does this set of vectors really form a basis? Are they linearly independent? So these are all the questions we should clarify now, and we are going to do here, and maybe we continue next time with. Namely, let us begin. And in order to prove that such a basis, first we prove that such a basis exists always, right? So existence, we will prove such a basis. And here, exactly this orthonormal basis we already discussed with you is very helpful. For we postulate, we take, because we work again in Euclidean space, and we prove with you that in this Euclidean space we can always find such a basis. And I take such a basis, and just imagine we have our original basis Gi. What I do now, I can Gj, this vectors Gj, they form a also a base. That means that every vector in this basis E is a linear combination of these vectors Gj, right? Because Gj vectors here, they form a basis. And every vector x, and including this vectors E, is a linear combination. Here in this linear combination, I use this components alpha. You see with two indices. Here we have a summation over j, and I index corresponds to, maybe I take another color here, and this, more carefully look here, this is index j, repeating once as a above script, once as a below script. It is a summation index, or called dummy index. And another index means that we speak about this index I, right? Okay, and we can do it in another way around. I clean again. We can do it another, namely, this orthonormal vectors E form also a base. That means that every vector in our vector space, including vectors G, can always also be represented as a linear combination of these vectors E. Again, you see here summation over J, right? Simply using this components beta, the buff index J is summed here, you see, and again, here this is a summation index J, and I means the number of this vector G, right? So you see these components here, they're rather interesting. These components alpha and beta, they have two indices. In principle, when we will discuss later with you a little bit, they can be represented as a matrices, right? We have index with we can organize this, values alpha like rows and columns according to the index size. But now it's not so quite important. Important is the following: that what I do now, look, I take here this EI and insert it here instead of this ij. The only I should be careful again. You see here summation over j, and here summation over j doesn't work. I change j to k. Maybe it is important also to note that summation index can be arbitrary index. I, j, k, whatever. You can use some Russian letters from Kirillitsa, right? If you want, or some other, any letter you want, right? Because it doesn't matter, because it is index takes the values from 1 to n, and how you call it, it doesn't matter. So we change simply the summation index because we apply Einstein summation convention, and this accordingly this summation index can repeat only twice. We cannot use it 3, 4 times. And here you see we have already j is already occupied. So what we do, we insert it here, and then we get this relation. And now you see we have here gi and we have here gk, right? We try to factor out, but it is different numbers. And what I do now, we make a trick. You will learn this trick in the exercises. Namely, if you look this term here, I have this term delta ki gk, right? You see k summation index. We sum up from 1 to n. So if you write out, it will be delta I1, G1, and so on, plus so on delta 1n, no, excuse me, delta n I gn, right? And in this whole sum, only one term will be non-zero, namely when I is equal to this number, right? Only term number I, because otherwise delta will be 0. Only this, if I and this above index are equal, this term delta will be 1, and only one term will here be active. That means that this will be exactly this gi, right? So you see here, I can artificially, before we skip this delta, you remember, and here I artificially introduce this delta in order to get exactly gi. So I can write here, or get this vice versa, excuse me, here, instead of here, I can express gi as a delta ki gk in order to get gk, because I have here gk and I have it here, and I can then factor out it, right? And as we discussed with you, introducing this delta, we represent in a sum in which only one term is not 0, but we substitute gi by gk, which is important. Why we do that? Because again, you see here, if I factor out gk, I get here, I move it to this gk, I move it everything to the right hand side with minus. And if we do that, you see we have interesting story again. We have a linear combination of this vectors gk, which is zero vector. But you can say, okay, vectors gk are linearly independent because they belong to a basis. How it is possible? The only what it can be that all these coefficients are zero. And which means that we get a very nice important relation that the, and by the way, be careful here again, we have summation over J. That means that beta times alpha is equal to Kronecker delta. If you write in the terms of the matrix algebra, product of the matrix beta and alpha is equal to the identity matrix, right? I write it here delta. We can also do it in this way, right? And this is very, very important. We see the connection between these coefficients alpha and beta. And now I have an idea how to represent these dual vectors. Namely, I take these coefficients alpha and apply again summation with my unit vectors. The only difference you see for convenience, I write these indices for this orthonormal vectors not below but above as a superscript, only to get the summation. But because I sum up, if you look at the beginning here, if you look, I clean a little bit here, you see here we sum up over this above index of alpha, right? This was above index. And here we sum up over the below index of alpha, as you see here, right? You see here, we sum up over J, below index. But we will just prove that so resulting vectors, this is a definition, is exactly this dual vectors, vectors dual to our initial basis. How to prove it? We simply calculate scalar product of our original basis and this vectors Gj. For original basis, we use this representation in terms of this coefficients beta. You see it was here, this one. And here we use this representation here for this vectors, right? We put it here. And you see alpha and beta can be factored out according to the axiom C3, I suppose, right? And here we have to apply, here we have to apply scalar product of this orthonormal vectors, EK, EL, which is Kronecker delta, right? Because of the definition of orthonormal basis. And if you look here, we have again the same story. We have double sum over K and over L. And we don't need this double sum because, as we discussed with you, this delta is almost always zero, except of one case when indices of this delta are equal to each other, right? And this is gives us possibility to exclude this delta, namely simply, you see here, simply substituting here L by K. For example, instead of L here, I put K, because L should be equal to K. If L is not equal to K, the whole term is zero due to delta. And the result will be this: if I substitute L by K and skip delta, this and this sum, and you see exactly this. We have summation here over, no, not correct, over K, excuse me, here over K, you see, exactly like before we had it here, exactly like here. Once more, I show you here, you see, here and here, and the result was again Kronecker delta. We discussed with you the product of these two matrices is equal to the identity matrix, which is expressed in terms of this Kronecker delta. And you see at the end, we have Kronecker delta indeed, which means that if you look at the beginning of this equation and at the end of it, we realize that these so constructed vectors, construct by means of this matrix alpha, they are really dual to our original basis, right? To our original. So clear, that means that we can always construct such a basis. Dual vectors always exist. We can construct them. Can you please explain GI, GJ part again? What does it mean, GI, GJ part again? I don't understand. What exactly should I explain? We first, what we did once more, maybe some to summary of this. We define with you dual basis here. GJ dual basis dual to our original basis GI, but we don't know where such a base exists. And what we do here, we use orthonormal basis. We always have in our Euclidean space, and we express this orthonormal basis in terms of our original basis, and our original basis in terms of the orthonormal one. Then we realize that these matrices of coefficients alpha and beta are orthogonal to each other, so to say, because of this relation product of this matrices is equal to the chronicle delta, or another way, unit matrix. And using this fact, we formulate our dual basis in this way by means of this orthonormal vectors. And we proved with you that this vector so constructed is then exactly what we need, exactly dual one. And this is what we just proved, and that means that we can construct such a basis. Now the question is, we cannot speak strictly about a basis because we don't know whether these vectors are linearly independent or not. Nobody said it. We have to prove first that these n vectors G, J above, they are really linearly independent. And then, if it is the case, they form a basis, right? How to prove it? We assume converse. We assume, on the contrary, you see here, we assume that there are some scalars, AI, not all zero, such that linear combinations of these new vectors we just constructed is zero. How to prove it? This is nonsense. We multiply both sides, not all zero, see here. We multiply both sides of this relation scalarly by our original vectors dj, right? You see here. And since here we have zero vector, this will be an exercise for you. We will discuss the exercises at the end. That maybe right here, if you have a scalar, if I have a scalar vector, scalar product of a zero vector by any arbitrary vector, it's always scalar number, right, for all x, right? And that means that if you multiply here both sides of this equation, we have on the right-hand side always zero. And this is what we start with here. It is zero. If we multiply by this expression by this original vectors gj, but Gi above and Gj, these vectors are dual, which means that the scalar product is chronicle delta. And what we get, AI delta ij, and again we have the same trick, where we have a sum over I, you see. But in the sum, only one term is not zero, where I is equal to j. So that means that we can skip delta and simply take this aj. And if you compare the begin of this equation with the end, you see that aj is equal to zero. But we repeat it every time for all these vectors gj, that we realize that under this assumption, all these coefficients aj should be zero, which contradicts to this assumption of the linear combination. That means not all linear dependency of these vectors, that not all scalars are AI are zero. And this is the contradiction we get. And that means that these vectors, they are not linear, they are linearly independent. They are linearly independent, right? Okay. So clear. And maybe the final step here for today, and we start shortly discussing the exercises, is the following, that we prove that such a basis is unique. How to prove it? Again, on the contrary, we assume that there are at least two bases, namely, I denoted this basis by G dash and H dash. And here you see G1, G2, Gn, H1, H2, Hn. Both of them dual to our initial basis G. Right? Different, two different, but both dual base. And how to prove that it's not possible, or they coincide, still coincide? Very easy. So again, I express one of these dual bases in quotation marks in terms of another one by means of some coefficients H, because all of them are bases, and we can express any basis as any combination of another one. And then again, we use the same trick. We form scalar products of this equation here. We multiply this equation scalarly by our original vectors Dj. And because both bases H and G, dash are dual, we get on the left-hand side Kronecker delta. And here we get a Kronecker, here Hi, right? It is written Hij is an Kronecker delta. And on the right-hand side, we have this equation here, this one. The only difference you see again, instead of summation index J, I substitute J by K. Otherwise, I cannot here apply, because J is already occupied. I cannot apply summation convention. And if I do that, again, you see, I clean a little bit here. You see here, I have a scalar product of vectors gk and gj, which are dual. That means that instead I can write delta kj. And again, you see we have summation over k and with delta, which means that in this sum over k, only one term is non-zero when k is equal to j. So that means that we still simply substitute k and j, and the result is simply Hij. And again, if you compare with the beginning of this equation, you realize that this coefficients are equal to Kronecker delta, which means that if you substitute here this Kronecker, if you write here in this equation here, I clean it. If we here, instead of this coefficients write delta Ij, then we realize immediately that these two bases we assume to be different. They in fact they coincide. They coincide, and we proved already with you, and this is a nice point to stop the lecture. We just only please connected. We discuss very shortly exercises. We proved with you the important theorem: to every basis in Euclidean space there exists a unique dual base. Very, very important, because we can always, like with the orthonormal base, if we have a basis, we can always construct a unique dual basis, right? You can ask me, what about orthonormal basis? If you construct dual basis to the orthonormal basis, could you write me some ideas? What do you think? What happens then? We said that to every basis there is a, in the meantime, I scroll to the exercises. We said that to every base there is a unique dual base. But if I start with the orthonormal one, what happens? And construct a basis dual to the orthonormal basis. Some ideas? Think about that a little bit. I think the orthonormal base won't have, no, not true. Is orthonormal base itself correct? Correct. There will be no difference. How you say orthonormal won't have dual? How it's supposed? We just prove that they always exist. right? This what you write, it contradicts what we just proved. We proved that to every basis there is a dual one, unique, and the orthonormal basis is also a basis, right? Correct. In this case of orthonormal basis, dual basis will coincide with itself. We'll discuss later with you also. Orthonormal base, in this sense, orthonormal base is self-dual. Let us shortly discuss the exercises. To the next Friday, we will begin with exercise 8:30. We will begin with exercises, and after the break at 12:30, we will have a lecture. Right, exercise 1.1, we discussed already with you. You have to prove these identities using only these 8 axioms, right? And this is we also discussed with you. If we have linear independent vectors, x1, x2, xn, you have to prove that none of them is zero vector. Then prove that any non-empty subset of linearly independent vectors is linearly independent. So if I have linearly independent vectors, I can take any vectors from them and they will also be linearly independent. This is also exercise to the summation convention, to delta, what we also discussed, especially with this formula, with the Einstein summation convention, when we have this index under the fraction bar. This is what we also discussed with you, scalar product with zero vector. Proves that a set of mutually orthogonal non-zero vectors is always linearly independent, very important for this as a result of this Gram-Schmidt procedure. We got orthonormal vectors, but we have to prove that they are linearly independent. This rule you know from school program, parallelogram rule, and please do this exercise. If you have some problems, we will discuss it with you with scalar product. This exercise is very important. How to prove that two vectors are equal. There is a very simple way to multiply both of them scalarly by some vector x, and if it is valid for all x, then this is proved, right? And you have to prove it at home. And maybe one numerical exercise, we start at least with you. Consider 3 vectors with these components with respect to orthonormal basis in 3-dimensional space, right? Component given with respect to orthonormal. And first, you have to apply first in the, right, exercise A here to construct the orthonormal basis using the Gram-Schmidt procedure. And then you are asked to construct this basis dual to it using this matrices alpha and beta, using this relation. And please stop here because the rest we have not discussed. So up to here, everything, please try to do that, everything, and we will discuss as much next Friday morning as much as we can. Okay, once more, if you have some doubts, please look the solution and we try to understand it, and then we will discuss with you. You will, by the way, prepare that you will present your solution, the exercise organized in such a way that you, in comparison to the lecture, you work, I rest, right? Okay, in this sense, have a nice weekend. If you have still some urgent questions, you can write me. Otherwise, have a nice week and see you on Monday for the пожалуйста, for this lecture, finite elements on Monday. Otherwise, see you on Wednesday, also lecture. There is another lecture, finite element method, or next Friday for tensor algebra. Right? Bye-bye.